Hello everybody and welcome to this video tutorial that aims to support students of GCSE astronomy. Now today's topic is all about tides, quite a small topic and one you'll be familiar with if you live on the coast. If you live inland then you won't experience this two high tides and two low tides every day. In fact, that's not quite absolutely correct. It's thought that the time interval between high tide and low tide is exactly 12 hours, but it's not true, because in the time it takes the Earth to rotate, the Moon has moved in its orbit a little bit, and the Earth has to do a wee bit of catch-up. So the actual time interval is 12 hours and 25 minutes. Now, if you are just confused by this, I've put this data in a little table, so this you will certainly need to know and be able to apply. So one lunar day is 24 hours and 50 minutes. So the 50 minutes is the Earth catch-up time. So half a lunar day, that's low tide to the next low tide, or high tide to the next high tide, is 12 hours and 25 minutes. And a quarter of a day, which is the time interval between a low tide and then the next high tide, or vice versa, of course, is half of that, which comes out to be 12 hours and either 12 minutes or 13 minutes. It doesn't really matter too much. Now, why are we fussing about the moon? Well, it's the moon that is chiefly responsible for the tides. And the reason for this is that gravitational forces, so it's all to do with the pull of gravity by the moon on the seas and the oceans of the Earth on a large scale. Gravitational forces follow what we call an inverse square law. Now, this was worked out by Isaac Newton, and he said that if you double the distance between two objects that are attracting each other gravitationally, then you'll find that the force of attraction is a quarter. If you increase the distance 3 times, the force is reduced to a ninth, and so on. So you can see the number is squaring, but it's an inverse property. In other words, the further away particles are that are attracting each other by gravitation, then the weaker the force. Now, if you look at this diagram at the top of the page, you'll see that there are effectively two diagrams. The moon's in the same place and the Earth's in the same place, but the diagram on the left I'd like you to look at shows the two forces by the moon on a piece of matter on the near side of the Earth, so that's indicated by a black arrow, and on a piece of matter on the far side of the Earth, and that's shown with the white arrow. Now I've deliberately drawn, and this is exaggerated of course, but I've deliberately drawn the dark arrow longer than the white arrow to show you that the force on the near side is greater than the force on the far side. Now, this has the effect of causing the Earth's waters, to some extent the Earth as well, but we'll deal with that when we look at tidal forces on interesting bodies like Io, one of Jupiter's moons. So, yeah, where were we? Yeah, this has the effect of effectively stretching the Earth, elongating it, as you can see by the diagram on the right. So the diagram on the right is the equivalent of the diagram on the left, and that's what the three little lines under each other mean. It's equivalent. Now, this is a simple explanation, and what I put in here is a little link to a NASA-based website, I think. Let me just click on this and show you that the link will work. Now, if you're watching this on the there we are. Sorry about the pause there. Here we've got this this little website, and you can have a look at this. Now, you won't be able to access this from the MP4 file, probably, and therefore, what I'll do, there's a worksheet that accompanies this video tutorial, so I'll put the link on so that you can use it and explore all this. There we are, the tidal bulge there. So that looks pretty good, and yeah. Not quite sure exactly where this has come from. I don't want to waste time in this video tutorial. So let's get rid of that. And hopefully we'll go back to what we're talking about. Yeah. So the waters effectively stay the same and the Earth rotates so that a place on the coast experiences a high tide and then a low tide, then a high tide and then a low tide. And there we go, quite a nice illustration showing Blackpool there in up in Lancashire, and that illustrates very nicely the difference between high tide on the left and low tide on the right. So a little bit for you to do, the pop quiz. It says on a particular date, excuse me, the high tide at a coastal resort occurs at 09:45 GMT. When should the next low tide be expected to occur? Right, well, you can cause the playback and be ready to receive the answer when you are ready. So just press the play button when you're ready for that. Well, if the time interval between a low tide and a high tide, if it's 6 hours, let's go to the generally accepted version by those who are not in the know, then the next low tide should occur 6 hours later. So 9:45 is 10, 11, 12, 1, 2, 3, which on the 24-hour clock is 15:45 GMT. But of course, we've not added on the time interval that we should do between a low tide and a high tide. So we've got to add on another about, if you remember, 12 or 13 minutes. So that gives us the next low tide expected at 15 hours 58. Now, at certain times of the year, we get what we call spring tides and high tides. Sorry, spring tides and neap tides. And spring tides are particularly high tides, and neap tides are particularly low tides. Now, in this tutorial, we really haven't taught much about the sun's influence, but when the sun and the moon and the earth are all aligned, so we're looking at the kind of time during which we might expect an eclipse, the sun's pull on the waters of the earth adds to that of the moon, and so we get particularly high what we call spring tides. Now, they are expected roughly every 2 weeks. Now, the neap tides occur in between, and these are tides that don't have a particularly high tide or a particularly low tide. So really, the pull of the sun and the pull of the moon on the waters of the earth are forming a right angle, and so effectively they kind of nullify each other. Well, the sun's influence nullifies that of the moon because the moon isn't really changing very much. Now, I put a little question in here. I think this will be in the worksheet as well, just to have a look at before we finish. So here's an example of an objective question, and this is found in the new Pupil Toolkit. So there we have the sun and the moon and the earth not to scale. And we're asked which of the following tides occurs when the positions of the earth, moon and sun are as shown in the diagram. So again, if you want to pause this and then play, then that will be fine. You'll be able to think about this a little bit. Well, what we're trying to show here is option C, that the moon and the earth and the sun, the angle between the earth and moon and earth and sun is actually 90 degrees. So they're at quadrature is the rather posh name for that. So they're forming a neap tide. So the sun is pulling waters on the earth to the left, but the moon is pulling waters on the earth upwards. And effectively, they don't quite totally cancel out, but they do tend to nullify each other. There are other factors, just before we finish, smaller factors that determine the tides of high and low tide. I think if you went to the coast, any place on the coast randomly, and had a look at what time high tide and what time low tide occurred, I don't think you would find this exact, to the minute. We had a few minutes ago, 6 hours and 12 or 13 minutes. There are other factors that affect the times of high and low tide, and I think you ought to be aware of these. So it does depend on, obviously, it's the movement of water that we're dealing with, so the shape of the coastline, and in fact, strong winds and other variances in our weather, such as high atmospheric pressure, do affect the motion of the moons as well. Good, so that's the end of the video tutorial on tides.